Hi, everyone. I'm George Levin, co-founder and chief business officer at AlgoX2, a data streaming operating system. In this podcast series, I am talking with our CEO and the creator of AlgoX2, Alexei Lebedev. My goal is to understand the technology we're building and the thinking behind it. Hi, Alexei.
How you doing?
I'm good. What's up? What's up in New Jersey?
We're digging ourselves out of all the snow that has been bestowed upon us.
I feel you. Same here in New York. We're just few miles from each other. I am in our New York office, and Alexei is from home in New Jersey.
Looking at squirrels.
Let's start. My goal again is to ask you some questions to use this opportunity to understand better what we're doing, and maybe for some listeners and YouTube followers, it will be interesting too. Let's start with the original story. Before AlgoX2, I know that you and Vlad, who is our CTO and the third co-founder, you built the trading technology behind the New York Stock Exchange. Tell us the story. What did you build and how did it happen?
Well, actually, the story goes even further back, I would say, because for maybe 10 years or so before I decided to write a financial exchange platform, I was doing high-frequency trading. And those were the innocent years before high-frequency trading even had a name. It was basically just connect your computer and try to get things flowing faster. And this is where I first kind of experienced the mess and chaos of distributed computing. Because if you have servers in several data centers, then you have state information on those servers that's you want it in one place. Okay, you want to know how many shares of the stock you got. You may have traded it in a data center in Carteret and then actually sold it in a data center in Hawken, but you're not aware of it. So how do you integrate it together? And the information arrives at different servers at different times, so you get out of order. You're seeing events out of order. It's almost like the theory of relativity, where two observers are observing simultaneous events as occurring at different sequences. So this was a very traumatic, in some sense, experience for a person who tries to build a system, because you're trying to do something coherent, but you're forced to use many small components because they need to be collocated with exchanges far apart from each other to be fast. But you want a unified whole. So you get this tension between many things and a single some sort of logical narrative around it. And now if we fast forward to the exchange it's fundamentally different from high frequency trading, but the thing that's unique about it is that it has to be very good at not losing information. One of the original reasons why we even decided to build an exchange was that there was an outage on one of the exchanges, and when we reconnected, we could not get the list of trades that actually happened. And later we received an Excel spreadsheet from the company containing that list of trades. And that really got us thinking, like, how is it possible that they have those trades, but they can't give them to us from the fixed gateway? And so we realized that they must have a particular architecture where the data becomes inaccessible when certain failures happen. And so we said, okay, if this thing is running in production somewhere in the US, then we have to fix this. We have to write an exchange.
That's a bold idea.
So New York Stock Exchange is running an architecture that is based on sequenced journals. It's essentially, I don't know how well this type of architecture is known or not known, because they don't really publish books on how to build exchange architectures. But in the file systems world, where data loss has long been sort of a dragon that everybody tries to slay, it's been known for tens and tens of years that if you don't want to lose something, then you have to use a journal. So the original NTFS, that's the system that came with Microsoft Windows, that was a journal-based system. ZFS, which is arguably the best file system today, uses a journal. And so the way we wrote the transaction engine for New York Stock Exchange is also based on journals.
It sounds really crazy that the New York Stock Exchange, which is a very established organization, is buying some new technology. How did you convince them? How did it feel, and how did it happen from the business side?
If you're not really honest with yourself and you introduce a bug here, hoping that it'll never happen, and it does, it might happen, that feeling is not very good. You really have to get some sort of level of confidence where you can go to sleep and know that you're not going to flip a bit from 0 to 1 in the wrong place and cause someone's balance to go up by an order of a million. Because depending where that bit is, it could either add a penny or $1 billion to their account if it's in the wrong place. So we are engineers, right? So we understand our limitations, and no one is infallible. So what we did was we used a formal method. We said, yes, we know how to write fast code, but the more you try to make it fast, the more error prone it becomes, because you're by definition taking shortcuts. You're not doing it in the simplest, most general way. So how do you reconcile this tension between wanting to write high performance code? I mean, you have to be the fastest exchange because all the other exchanges are competing with you. Only the fastest one gets the orders, right? How do you reconcile this tension between having to be fast and having to be correct? And the answer, the unambiguous answer in our mind, was that we have to build a code generator that would emit code that is correct by construction. We did that. We open sourced it. And when we went to New York Stock Exchange, when we sold our technology, we left there was a copy of it in open source. And later, when I was leaving New York Stock Exchange, the CTO, who is a very nice guy, Mayur Kapani, he said, yeah, why don't we open source the improvements that you guys made to this code generator inside NYSE so that they don't diverge and so that they can be easily supported later. And we did that. And so today's startup, our X2 platform, we're building with the help of the same code generator. It's an open source system that takes some relational tables and translates them into C++ that doesn't have errors. And it generates, checked this morning, about 1.6 million lines of code in the X2 code base right now. In a couple of years, it's going to be several million lines of code. And so the further you go, the more dividend it pays to use a formal method like that.
Yeah, there will be definitely another episode just about OpenACR, because I'm really fascinated and really want to understand better how it works and what it does. But right now, let's get back to the original story. So you had one of the most demanding data challenges running on your architecture. What inspired you to leave and start AlgoX2?
There comes a time in software architect's life when you look at all the code that you wrote and you see how much of it is getting into production, and you realize that your job is done. I think your job is done when you're not adding to the production code base anymore, because you've really done it. It's very simple. So once you spend a year and a half in this mode where like there's really nothing you can add, you realize, okay, either I'm going to sit there and watch my 401k grow, or I have to go and do something more useful.
Yeah, we know a lot of people who prioritize number one, but no judgment here. Let's talk now about AlgoX2. So you often describe AlgoX2 as a data streaming operating system, as a message-oriented middleware with streaming platform APIs, as a transactional platform, as an append-only file system. So tell us more. So what is it and how you look at it, like as a big picture?
It's a data streaming platform, meaning that it takes connections from the outside, from so-called producers and consumers. And producers send messages that are saved to stream files inside, and consumers subscribe to messages by indicating what range they want to read, and the system serves the messages out to the consumers. It's very simple to explain. Now, where does the complexity start coming in? Well, first of all, you have to be able to do this at a high message rate. If producers are sending you several gigabytes of data per second and consumers are not able to keep up with that flow and are reading some older messages as a result, your system should not be back pressuring the producers and preventing them from writing further data. So it should be the consumer's problem to keep up. And similarly, if consumers could be very fast at reading and as a result putting a lot of pressure on the system to send data out. For instance, there's something called fan out, which is how many times a message leaves the system. You could be publishing a message once and the fan out is 10, so 10 people are actually reading it. So if the system is not able to properly load balance the consumers and send that message to all 10 of them, you're going to be slowing down all of them and they will fall back even though they're actually really fast. So there are lots of data flow challenges presented by the mere formulation of a problem like this, that you have to publish messages, decouple producers and consumers. They independently come and go, and be able to serve them whatever requests they send your way. The reason we call it an operating system is because there are many, many problems. Essentially all problems involving more than one computer can be separated into two layers. The first layer involves taking unordered events and producing some ordered sequence out of them. And the second layer involves taking this ordered sequence and deterministically interpreting it to produce some result. This has been done very successfully. So first of all, it's been done in exchanges. It's been done in databases, so-called run-to-completion databases, which are very stable and have very nice properties. They work this way. First, what they do is they simply they collect all the inputs and they order them. And that's all they do. They form a journal out of the inputs. And then this journal determines how the transactions will run and the transactions are executed to completion. This has the benefit that once you form that journal, you can spread it out to any number of nodes, and those nodes could execute in parallel without ever communicating with each other. They have been essentially externally synchronized. That's a very important property. And you can predict what sort of conflicts or rollbacks will occur without ever forcing communication between these nodes just by looking at that journal. The blockchain is a famous example of a ledger or a journal. They don't call it a journal. Every generation has to pick a new fancy word for it, so they call it a ledger. It's the same thing as a journal. Same exact. So blockchain is famously decentralized, but in fact it is actually centralized. It's the fact that it's centralized that allows the subsequent decentralized participants to do their thing. The marketing point is that it's decentralized. Actually, it's not. It's so centralized. It's way more centralized than even, a financial system consisting of just two banks, because those banks operate independently of each other. You can never know what the balance is with this participant A if you're a participant B, because A is executing its own transactions without notifying. So that's a decentralized system. But in Bitcoin or blockchain, it's always predictable because every single transaction has to go through the same place. So it is in fact centralized. But that's a good property. The fact that events are ordered, are brought from all over the world into a single place, put into a sequence, and then everything else happens after that sequencing has been done. That's a very good property. So that's a property that that's what I call the layer number one. Layer number one is you want to sequence things and produce some sort of deterministic order. Here's another way of looking at it, okay? The number of ways to interleave n events is n factorial. As we know, even the number of ways to interleave the number of shuffles of a deck of cards is greater than the number of atoms in the universe. So 52 factorial. It is such an insanely large number, even for a tiny n like 52, that if you're talking about n equals a billion, which is a very small number in data streaming platforms, a billion messages is nothing. The benefits of that single ordering far, far outweigh any sort of drawbacks that sequencing may have, such as bottlenecks. So that's the layer number one. And layer number two is you start executing some functions as a result of receiving that stream of data. I could give various examples of what sort of problems can be solved this way. So for instance, a data streaming platform is a great control plane. You could send commands to some stream and then have subscribers subscribe to that stream and just execute the commands as they are issued, as they are read from that stream. And that's essentially a way to control a group of computers. You think of the data streaming platform as a sort of network overlay for a number of computers. So you're taking a bunch of servers and you're turning them into one with a single tool. Especially today, we have so much AI going on. It's generating so much data that nothing fits one computer anymore. Everything is a cluster, right? You're talking about data flows that are very fat with lots of events, even inference. You're talking to a chatbot, you're talking to a whole rack of servers because it doesn't fit a single server. So it is really fundamental to be able to turn that collection of servers, whether it's 72 or 300 or even 2, into a single logical entity and to talk to it in some simple way. And we really don't have a lot of tools in this area, believe it or not. So the streaming platforms of today are largely concerned with just getting the messages into some log form, into some journal form, and then serving them out eventually. And we're talking about latencies of thousands of milliseconds and even more. You want your system, in order to be usable as, let's say, a control plane, you want it to be as interactive as a computer. So it has to operate on sub-microsecond level at least. It has to be able to do millions of messages a second, and the messages have to be, the latency tails have to be very predictably low.
Got it. Yeah, thanks a lot. I think this was our first episode. It was very cool. We shared a bigger picture. And in the next episode, we'll talk about details of our architecture. We'll explain how it works, what's so special we have in it. Thanks, Alexei, and see you soon.
My pleasure.